What we want to know is how good are LLMs in figuring out what, for example, the edge cases are. Let's see what the results are. And this is 25. Okay, so there's about 25, 25, 35, and we have 26. Are you sure? The question is, how do we do this the adult way? If we start to go in deeper, things are getting much more interesting. Hi, everyone. My name is Denis, and I work at Imandra. And today I wanted to speak to you about LLMs, how they're used in AI-powered software development, their fundamental limitations, and how they manifest themselves in the tools that use them. But fundamentally, also discuss how we can alleviate these issues by introducing this other type of AI. One way to refer to it is the good old-fashioned AI. Kind of more modern definition is automated reasoning, formal methods, but ultimately it's a set of symbolic techniques that help us analyze software to bring in mathematical rigor. So instead of using kind of statistics that change from one application to another, we get something that's fundamentally precise, a mathematical model that can help us generate code that we can reason about, understand, and ultimately deploy in safety-critical applications. So before we go too deep into the process, I wanted to start out by doing a simple case study. So let's look at a bit of Python code. So we have this. This is just encoding some business logic from a financial application, in particular, financial exchange called Six Swiss. And all this is doing is looking at order book, which is a list of buy and sell orders, and determining that if a trade is possible, what would be the price of that trade. As you can see, there's some somewhat convoluted logic when it comes to what the conditions are that lead to a certain outcome. You can see in some cases there may not be any price at all because the trade is not possible. But what we want to know is how good are LLMs in figuring out what, for example, the edge cases are. How can they identify these things? So we have a collection of our favorites. Let's start out with ChatGPT. So let's ask, hey, how many edge cases are there in this code? All right, so we have this guy going. Let's now go to Claude. All right, and last but most certainly not least, so this is also using Claude, but slightly different version, and obviously with different, let's say, prompt and all of those things. But what I want to ask is, how many edge cases are there in Six Swiss Python code? Okay, so we have all three going. Let's see what the results are. So we have, interesting. Okay, so final answer for ChatGPT's 26. Okay, and they've done this arithmetic. What if we go to Claude? How many do we have? 25, 35. Okay, so 26, 25, 35, that's a pretty decent kind of convergence, and this is 25. Okay, so there's about 25, 25, 35, and we have 26. Let's ask this, like, are you sure? So what it comes back with. Are you sure? A lot of the answers that these tools give are always also a function of temperature and various other things like this. So this is now 34. So we just had, what was the input? So I had 26. And then we ask, are you sure? So that jumped up to 34 total, 34. Okay, I'm not going to torture it anymore, but let's look at what our friend Claude is telling us. Originally, we had 25-35, but now it's actually saying, you know what, it's 5, 6, 7, or 8 true edge cases when the system might be unexpectedly turn on. Okay, and what does cursor tell us? Cursor tells us 25, so I'm not going to touch that. So we have this range. After second thought, Claude came back with 5-8 true edge cases. Originally, it was 25-35. Now we have ChatGPT that comes in with, what is this, 34. Originally, it was, I believe, 20-something. Let me see. Yeah, 26, but now after second thought, it was 34. So ChatGPT went up in terms of edge cases. Claude went down, and we haven't touched cursor. So basically, I think if we were to use this, let's say, model where it's a mixture of experts, we can say that the number of edge cases is anywhere from 5 to 34, given the kind of the sample that we've been provided. So the question is, okay, how do we do this the adult way? How do we, instead of just kind of looking at statistics and relying on these guesses and this distribution, we get to something that's precise and rigorous? And yes, let's go to our friend slide deck. And what we're looking at is, so this is where we're at right now. You roll the dice. Sometimes you get 20, sometimes it's 5-8, sometimes it's 34. If we're to repeat this experiment, we'll probably get very different figures again as well. So this is where we're at. What we really want to get to is this stage where instead of us rolling the dice and kind of seeing what all of this output can mean, what we want to do is we want to leverage LLMs and their ability to translate, in this case, from Python into mathematics, and I'll tell you in a second what that means, but then leverage symbolic techniques that use logic to actually tell us the answer to these questions and other types of questions, but we'll primarily focus on analysis of edge cases in code. And to do that, I'm going to talk about two things that our company works on. One is Imandra, the latest version called ImandraX. So this is an automated reasoning engine for analysis of algorithms by translating models or programs from input language, which is called IML, Imandra Modeling Language, which is a subset of OCaml, into mathematical logic under the hood. And then being able to apply all sorts of rigorous techniques that are logic-based that can give us precise answers to those questions we're just asking those tool providers. So that's the first. And the second is this agent that's more recent, something we've been working for the last few months, that uses LangGraph. So it's an agent that's built in LangGraph. And what it does is it helps us with this process of translating from Python, from Java, all these other languages into precise mathematical models in IML. And then it uses Imandra, obviously, in the mix to when it does that translation, along with other formal tools and LLMs and databases and vector databases and things like that, but also is able to use it, for example, to identify any flaws, generate what are called verification goals, and analyze edge cases and things like that. So those are two things that I'm going to walk you through today. Okay, so I'll start by introducing ImandraX, and ImandraX has many features, but the really two important ones for our discussions here is being able to formally verify properties of source code. And so when we're talking about formal verification, what we mean here is taking a model of that we wish to verify, for example, source code that I'll show you in a second, and then also a property that we wish to verify. And then the engine logically reasons whether this property is true or if it's false. And if it's false, it comes back with a counterexample. So, so that's the first important feature. The second important feature, and this is the one that pertains to the question that we're asking all those tools, is something called region decomposition. So region decomposition takes a model written in IML and automatically generates a number of edge cases that describe the state space of that model. And it does so not by any statistical technique, the same with formula verification, but actually through rigorous logical analysis of the model and the state space. And this is what we'll use today together with CodeLogician to identify and being able to answer all of those edge cases. Okay, so why don't we start to go and look at what does ImandraX look like? So this is our original Python file. Let's look at some simple programs. So what you're looking at here is VS Code extension for ImandraX that you can download. So I'll provide all the links below. But you can use obviously the same extension within Cursor, which is what I'm doing. You can sign up. So the extension will require for you to install CLI, which the instructions are also there, and get an API key. You can get that. There's a free tier in something called Imandra Universe for that. Again, all the instructions will be provided below. And what you're looking at here, this is a fragment, very simple example of writing IMLs. Again, a pure subset of a camel that is the kind of the core input language into ImandraX. So in this first fragment, we have a function g that takes x as input, and if x is greater than 22, then it returns 9. Otherwise, it's 100 plus x. So obviously very basic example, but when we talk about region decomposition, ultimately that's what we're going to use to think about the number of edge cases. We're going to want to take a model and then automatically identify the edge cases. So if we're just to, this is the decomposition command in ImandraX. If we're to run this, visualize this, we would get something that looks like this. So once we print out details, we can start to look at the resulting regions. So that function, as expected, has two regions that were automatically identified by ImandraX. So the first region is that both regions have a set of constraints and the invariant result. So what this means is that when this is not true, so when x is less than or equal to 22, the output of that function will be 100 plus x. And you can notice that the constraints and the invariant result here are both symbolic in the sense that we're not saying that there is a specific value of x, like let's say 0 or 10 or minus 100, that only fits this. We're saying that for all x, such that this constraint is true, when we run that function, the output of that function will be 100 plus that value. So again, this will be 22, because this is not x greater than 22. So it can be 22, 21, and everything to very negative number. The other region of this is the other region contains x greater than 22. And when the function is called with input that satisfies that constraint, the output will be 9 always. So you can see with not only has ImandraX basically broken down the function into those regions, and we'll see how this works with functions that are, or models that are much, much more complex and, for example, can contain recursion and lots of other things. What it does when it describes these things, not only does it actually symbolically describe those edge cases, but it also can give us a mathematical proof that says that if you combine all of these regions together, you get the original behavior of the function itself. Okay, so that's region decomposition. We'll show in a second what this looks like in a very simple case. this is a very simple case, and now we'll go through something that's more advanced. But to finish off the kind of the gentle introduction to ImandraX, this is region decomposition, so analysis of edge case as a function. And the other property is formula verification. So here we can define a property. So for example, this is just saying that anytime x is greater than -50, will always be the case of g of x, so this function here, with that x is greater than 0. So what we've done here is we've written a verification goal, and Imandra has verified it. You can see there's a happy Imandra face here. And there's all sorts of information that you can view that explains the reasoning that Imandra used to arrive at that. Similarly, if we write something that is not true, so for example, this, we get a highlight and says, actually, here's a counter model. Consider this number, minus 100. And for that number of x, this will be false. So you can see here, not only do we get proofs, but we get automatically counterexamples. And for other applications of CodeLogician and ImandraX, this comes in very handy when we handle much more complex models. Things like this. So we have lots of examples online where we look at very deep properties of code that we wish to verify. And especially when you're working in safety critical industries like finance and avionics, etc., you really want to make sure there are no missing or no edge cases that you haven't considered, because if there are and you find out about them in production, bad things can happen. Okay, so we've looked at basic examples of how you use ImandraX, how you get region decomposition, but now let's go back to our original Python code. And we want to now think about, okay, what would it take for us to rigorously think about how many edge cases there are here? And this here is, let me just switch the context. So we have an agent, and this is, let me go through cursor settings. You can see I'm going to use the MCP integration. So this is CodeLogician. We're now connected to CodeLogician from the cursor. I'm running this locally, but right now it's May 21st. By May 25th, we should hopefully have this up and running live that you can connect to. But even if you're watching this before that is released, we already have VS Code extension that you can use for CodeLogician and effectively repeat this process that I'm showing you right now. This is just the next iteration of how you can use this with MCP. But even without MCP, you can use this straight up as a VS Code extension today. And again, I'll provide the links below the video. So we have CodeLogician. It's good to go. Let's go back to our friend, this Python code. So let's now ask cursor to say, learn about CodeLogician. So what it should be doing now is it's calling the MCP tool. So one of those tools is system prompt that will teach cursor about how you could go and use this. So it's getting some information about what is IML, how you write code there. And it's now going to explain this to me, which is it's very useful. But fundamentally, what we're going to ask it to, let's do this. Use CodeLogician to take 6 Swiss code and generate an IML model using agentic flow. Let's see what happens here. So what it's now going to do is it's now connecting to this LangGraph-based agent. It's giving this code from 6Swiss. And what it's going to do is it's now going to Yes, it's initializing the state. It's basically going through all of those steps within the agentic flow to create an IML model for us. And the agent itself, so we have all of the documentation, tutorials, and things like this that explain how it works. But the high-level overview is the agent has a bunch of agentic let's say workflows that really, let's say, go from Python and then use its internal vector database with examples of various tools, ImandraX, etc., to arrive at a model. But you can also do kind of low-level steps that, for example, override the type of information. Let's say you have an incredible static analyzer for your code, or you have some information that knows something that CodeLogician wouldn't. You can always insert that information into CodeLogician, so it can use that when it's formalizing this stuff. So when it's running like this, one term to describe what it's doing is auto-formalization. So we're going from something that's informal. In this particular case, it is this Python code. And we're creating a formal model, so mathematically precise logical model. You can see here, it's already kind of arrived at something. So okay, so now we have an IML model, and what it's done is it has completed all the various checks. So when it does that, not only has it generated it, but it's also, at the end, just checked against ImandraX to make sure the model is admissible. So all of this is happening behind the scenes using APIs, etc. So yes, let's now do the following. So let me just resize this window a bit and say, okay, save the resulting IML model to a new file. So it's now extracting it from the state of the agent. And it is now going to generate an IML file with that extension. Let's try to see what it's now doing. But it should be just basically writing this file because it has all of that information. Okay, so let's go and accept. And what do we have here? We now have this 6 Swiss IML model that was generated from the Python code. So this is what CodeLogician has done. It has basically looked at this Python code and told us that this is a functionally equivalent model, just an IML. Well, now that we're in IML world, we can use our IML extension. So let's go do that and try to, its cursor is very helpful. It's already telling me what I should be doing, which is now decomp. So now let's go through this, and you can see here this command has already just finished, so lightning fast. And now let's go and visualize this. So very interesting. So let's look at the same map that we just looked. Remember that function was very basic on only 2 regions. Now these things are getting more complicated. Oh, interesting. So what we're now saying is that the top level region here is, so this is not empty. So this just means that the buys are empty. So no buy orders. In this case, that the invariant result here is saying none. So there's no price because there are no buy orders. Okay, that makes sense. Now let's go into kind of deeper things. Okay, now you're seeing here that this is basically the constraints that go into all of these regions are cases where they're both buys and sell orders. So all of these constraints, you can see they're expressed in IML, and they were automatically generated by the reasoning engine. So there's once you get into the world of IML, all of the statistics goes out the window. You have precise mathematical logic. And these constraints were generated by ImandraX. So if we start to go in deeper, you can see here, things are getting much more interesting. So let me just resize this guy. you can see these constraints are pretty intense. Let me just kind of move this out of the way. So again, this is pure IML, and I will show you in a second how Cursor can take this information, not only generate test cases, but also explain what what actual edge cases are and what they're doing. But if you're going through this code, what it's telling you is in this region, so both the buys and sells are not empty. This is great. So this is saying that the head of buy, so the best buy order is limit, not. So it's basically, it's not limit. It's now saying yes. So it is in fact market. So this is, they're saying the same thing. We are saying head of buys is not quote, all of these things. We're also saying that the tail of the buys and sells is not empty. And we're also getting these very interesting things where right here it's saying that the head of the sells limit order is less than or equal to the reference price. If all of these things are true, then we get into this region. And this region gets us this invariant result, which means that if we run that model on inputs that satisfy all of these constraints, then the output will be that the fill price, which is the output of that function, will be the limit price of the second best sell order. So this is the head of the tail. So a tail just means the everything except the first, and the head means the first element of that residual. So second best limit price. If we look at the adjacent thing, you can see the constraint just slightly changed right here. You can see that this constraint with the cells, it is exactly the opposite. And in this case, the output is a reference price. So you can see this is the type of reasoning that you can get automatically. And the LLM output that we watched before, that we've seen before, doesn't come close. It doesn't come anywhere close to this. So if we start to zoom out and we start to think about, okay, we have contained regions. There's 43 here. So there's two. So this is one. And in this subregion, so this is, think of it as like a tree. So not, we just care about leaves. But we have, something 43. So we have these things and then direct, etc. So you can, depending on, kind of granularity and things like this, you can have, so you really get with 44 regions of this code. So that is the answer if we're thinking about this logically. So, okay, this is great. What can you now do with this stuff? If we go back to IML, actually 6 Swiss, our old friend Cursor. Now let's ask this process that we just have done manually by decomposing a function. Let's also now ask Cursor to speak to CodeLogician to repeat this process, but ultimately generate test cases for us in Python that we can go back to this original code. So let's do that. Let's use CodeLogician. We don't have to do it, but let's just be more precise for the sake of demos. CodeLogician to decompose match price. So it is now calling a command within CodeLogician to perform what we have just done manually. And it is now getting formalization summary, which is a way to, you can see, generate test cases. Here we go. Okay, so let's just see what is the, Yeah, so this is, you can see here, we're just accessing the state. So the CodeLogician agent itself, it is stateful, and all of these commands that we run basically modify that state. So, and you can also modify it directly, for example, by changing, let's say we want to change this Python code, but we want to then rerun the full analysis. We're not going to start from scratch. We can just say, hey, I just made the changes to the source program. Let's now look at everything else, but reuse the information that was already generated before. So what has it done? Get state, region decomposition. Then let's say writes out tests for the full let's call it all of the regions of managed price as a separate Python test file. Let's see what it does to this. So now it should hopefully be generating test cases based on this rigorous mathematical analysis. And if we were to go and accept this, we will start to get all of these guys right here to do this stuff. So here we have it. And if we were to, let's say, save region decomposition results as a separate file, we should also be able to get that. I just also match price region.json. So the data should already be within the state of the agent itself. We should, all the time is taking right now, should just be cursor writing this into a separate file. So let's wait just a bit more to see what's happening here. But we should get this file soon, match price regions.json, that contains all of those regions that we wanted to. And if we're just to look at this, let's say we accept it. Yes, document all of the match price from region definition test cases. Okay, and here you go. So all of these constraints, you can see description, everything that we just spoke of are now as its own JSON file, basically. And you can see here, for example, test cases. So these are test cases that were generated by ImandraX. And you can then use them to generate test vectors. And in a separate video, we'll show you how to slice and dice the state space. So for example, you can look and say, hey, I just only want to consider certain aspects of the state space. I want to change something. There's many different techniques that allow you to really kind of operate with this region decomposition and fine tune it to be whatever you want it to. But the fundamentally is what you get out of this is something that's rigorous, something that you can use in software development, especially if you're writing something that's safety critical. So that is all for me. And please go to Imandra.ai and start verifying your wipes if you're into wipe coding. So thank you. Bye.